So, section 14.5, chain rule. Recall, suppose I have y is a function of x, but x is a function of t. Then define the derivative of y with respect to t. I just use the chain rule. It's a derivative of y with respect to x times the derivative of x with respect to y, with respect to t. The dx's cancel in Leibniz notation. Or in non-Leibniz notation, the chain rule says the derivative, maybe I should put the little, let's do it like that. The derivative of f of g of x, of the composition, so if you look at f composed with g, and you take its derivative, then it is the derivative, it's the composition of f prime composed with g at x times the derivative. So the chain rule says, well, it's a derivative of the outside function. Evaluate the inside times the derivative of what's inside. Let me give you some notation that we may use. D sub vector A, v comma w, where v and w are normed linear, norm vector spaces, complete norm vector spaces. They're actually Banach spaces. Where v and w are vector spaces. F, this is, so d sub a, v comma w is just the set of all functions f from v into w such that f is differentiable at the vector a. So let me do the chain rule. Suppose g is a differentiable function at a from the vector space v into w, and suppose f is a differentiable function at g of a, where f goes from w to the vector space w to the vector space x. Then f composed with g, a vector space from v to x. This will be a function from the vector space v to the vector space x. It'll be differentiable, and the differential of f composed with g at a is just the differential of f evaluate g of a times the differential of g at a. This is actually the composition, but when you look at the matrix representation for a differential, the composition, since these are linear functionals, the composition of linear functionals, the matrix representation, let me restate that, the matrix representation for the composition of linear functionals is just the matrix multiplication of their matrix representations. So even though this says composition, which it should, it really will be a multiplication when we actually do it out. So that's why in here it's multiplication. So let me do this in a particular case. So suppose z is equal to f evaluated at x and y. Then, and suppose x is g of t and y is ht. And all of these are differentiable. So f, g, and h are differentiable functions. Then z will be differentiable in t, and the derivative of z with respect to t is just the partial of f with respect to x times dx dt plus a partial of f with respect to y times dy dt. So you just take the partial of this with respect to x, partial with respect to y, and you have to multiply. Well, if you take the partial with respect to x, then you have to multiply by, well, the partial of x with respect to t, but since x only depends on t, we don't call it the partial of t because it only depends on one variable, so we call it dx dt, plus a partial of x with respect to y times a partial of y with respect to x. But again, since y only depends on t, we call it dy dt rather than partial of y with respect to t. So let's do another chain rule. Suppose, so this is just explicitly writing out the matrix representations for this. So I'm just giving you several differing particular cases that usually we'll be using. So let z equal f xy, x equal g st. Ooh, so when you do the partial, it really will be a partial. Y equals h st. Suppose all these f, g, and h's they're all differentiable, and everything else is just differentiable. Then z is differentiable in s and t. So let's take the partial of z with respect to s. Note, up here, we just call this partial of z with respect to t, dz dt, because z here only depended on one variable t. So that's why we didn't use the partial notation. Here we have to, because it depends, z will depend on both s and t. So the partial of z with respect to s is the partial of f respect to s, which is going to be the partial of f respect to x times partial x with respect to s plus a partial of f with respect to y times a partial of y with respect to s. The partial of z with respect to t is the partial of f with respect to x times a partial of x with respect to t plus a partial of f with respect to y times a partial of y with respect to t. Okay. Oh, so we can state this in general. So you should notice that each of these, and maybe I'll just sort of state it here, that this looks like, actually, maybe we should even write it here. Oops. Oh, ooh, I gotta end in about 2 seconds. Okay, so let me just state it. Okay, so it's going for, so this is equal to the partial of f. I gotta end this pretty fast. Respect to x, partial of f respect to y, times a dot is a dot product. And I'm gonna, this is x, the derivative, xy. This is equal to the partial of z respect to x, partial z with respect to y, dot, this is a dot product, partial of x and y with respect to s, with respect to t. And so, in general, it'll always have this form, and I'll have to state that tomorrow. Okay, so that's it for today. And any questions? Any questions? If not, I will stop the recording. Okay. So let U be differentiable in x1, x2, xn. And each of these x of i's are differentiable in t1, t2, t3, dot, 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 up to t sub m. Then U is differentiable in t1, t2, t3, dot, 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 to tm. And explicitly, the partial of U with respect to ti is the gradient U dot the partial of the x vector with respect to ti. It is symbolically can be thought of as the vector where I take each of the partials of U with respect to xi, so partial U x1, comma, partial U x2, comma, partial U x3, dot, 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 to partial U xi, dot, the vector, partial x1 with respect to ti, partial x2 with respect to ti, partial x3 with respect to ti, dot, 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 partial xn with respect to ti. It is partial u with respect to xi times partial, start that over again, partial u with respect to x1 times partial x1 with respect to ti plus partial u with respect to x2 times partial x2 with respect to xi plus partial u with respect to x3 times partial x3 with respect to ti, dot, 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 partial u with respect to xn times partial xn with respect to ti. It is the sum j equaling 1 to n of partial u with respect to xj times partial xj with respect to ti. And this is going to be true for all I equaling 1, 2, 3, dot, 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 to m. Let me tell you about the implicit function theorem. So let U, V, and W be norm vector spaces, Banach spaces, and let F be a mapping from an open set A cross B, the Cartesian product of A and B, of U cross V, the Cartesian product of U and V, to W. Suppose that F is a continuous mapping from A to B, implicitly defined by the equation F x comma y equaling 0. And suppose F is differentiable at AB, where B is f of A. And that the differential of the second component of F evaluated at AB is invertible. Then F is differentiable at A, and the differential of F at A is equal to minus the differential of the second component of F at AB inverse, composed with the differential of the first component of F at AB. So let me actually do this. Oh, and remember that if I look at the matrix representation for this, then this is going to be matrix multiplication. And this first one will be the matrix inverse times the matrix, another matrix. Okay, so let's recall this for what we did back in Calculus 1, and that will show you, that's what this is. Okay, so that's this guy. And so x squared plus y squared equals 1. Let's take the derivative of both sides of this equation with respect to x. And so this is just going to be, well, the derivative of x squared, 2x, derivative of y squared, 2y, dy dx, is equal to derivative 1, which is 0. So let's solve for dy dx. And so I get that dy dx is equal to a minus 2x divided by a negative, divided by 2y. Okay, so this 2x here is just this df1. This minus 1 over y is the negative the inverse of the second component, the differential of the second component of f. And so that's that dividing by a 2y. Okay, so this formula here is what we got previously from looking at implicit differentiation back in Calculus 1. Okay, so let me look at an example where suppose I have f, and it'll look a little bit more like this here. So suppose I have f of x comma f of x equaling 0. And suppose that the partial of f respect to y, when I say that, I mean the second component, and maybe I should write it so it looks more, oops, like what I've written above. So maybe I'll say that's the second component, and I'll say this is the first and second components. One, two, right? Yeah. Okay, so now, oh, and maybe I'll write it this way actually, because then it'll actually really look like it. Okay, so so suppose f of x comma f of x is equal to 0. And suppose that the second partial of f with respect, the partial derivative of f with respect to the second component, this part, is not 0. Then let's take the derivative of both sides of my equation. Actually, I should write it this way. So this is just going to be the derivative of the first component, so the partial derivative of f with respect to this first component, plus the partial derivative of f with respect to the second component, times, well, the derivative of what's inside, f prime. So let's bring this f sub 1 to the other side of my equation, so I get a negative f sub 1, and divide by f sub 2. So notice I've written it the same way, that this differential is minus the inverse of the differential of the second component times the differential of the first component. And so this is, in this particular case, the implicit differentiation. And so even though it's explained slightly differently, what you did back in Calculus 1, this was the Calculus 1 formula, written sort of in our notation. So let's do this for the following. Suppose I have f of xy, f of xy equaling 0. So now I have that capital F here depends on three variables, or has three variables here, and this third variable is a function of these first two variables. So implicitly, it really is a function of two variables. And suppose that the derivative of this third component is not 0. Then let's take the partial of both sides of this equation. Let's first say with respect to x. So this is going to be the partial of f with respect to the first component times, well, the partial of x with respect to x is 1, plus the partial of f with respect to the second component times, well, this doesn't depend on, I'm going to assume that the partial of y with respect to x is 0, plus the partial of f with respect to this third component, times the derivative of what's inside, which is the partial of f with respect to x. 0 with respect to x is just 0. Okay, so let's subtract f1 from both sides and divide by f3. And so, again, this looks like what we had from above, and maybe I'll write that, a negative 1 over f sub 3 times f1. Okay. In this case, now when I say, I guess I should have explained what I mean by, so when I said the first and second components, I meant that I split this up into two pieces. And so the first component could be several things, and the second component could be several things. So this could be like j variables, and this could be m, k variables or whatever, just so that the I plus j, or I forget what I call these, add up to the total dimension of this. Was it m? Whatever. I didn't say how many dimensions. As long as it comes up to the total dimension of your original f. So in this case, this was one of the components of this first one, in which actually consists of two variables. So now let's do the partial of this respect to y. Okay, so it's a partial of the f respect to the first variable times, well, 0, partial of this respect to y is 0, plus the partial of the second component of capital F times the partial of y respect to y, which is 1, plus the partial of f respect to the third component times the partial of f respect to y. So again, to solve for partial of f respect to y, this is just going to be, well, you bring the negative f2 to the other side of your equation. So we get negative 1 over f3 times f2. Okay. So again, it has the same structure as the theorem I gave you. Okay, so let's do some examples. On page 983, in exercises 1 through 6, use the chain rule to find dz dt or dw dt. Okay, so in this case, z is equal to x minus y divided by the quantity x plus 2y, where x is a function of t, e to the pi t, and y is equal to e to the negative pi t. Okay, so first off, let's figure out the chain rule. Obviously, it's not a w, this is a z. So dz dt is equal to, well, z is a function of x and y. So this is going to be the partial of z with respect to x. But x is a function of t, and it's just a function of one variable. Since it's only a function of one variable, rather than writing partial x, partial t, since here x only depends on t, we write dx dt. Plus, well, again, z depends on y, so this is the partial z with respect to y, times, again, dy dt, since y here only depends on t. There are no other, z doesn't depend on any other variables, and so that's it. So let's figure out each of these. So let's figure out dz, dx, curly, let me just say that again, curly z, curly x. And so I'll use the quotient rule. So it's the derivative of the numerator, 1, times the denominator, x plus 2y, minus the numerator, x minus 1, all divided by the denominator, x plus 2y, quantity squared. And so this is the partial of z with respect to x. So x plus 2y minus x plus y over x plus 2y quantity squared. Obviously, the x's cancel. And so I get the partial of z with respect to x is equal to 3y over x plus 2y quantity squared. Okay, let me get some more room here. Okay, so now let's determine dx dt. Well, x is equal to e to the pi t, and so this is just e to the pi t times the derivative of the exponent pi. Let's find the partial of z with respect to y. And so, again, let's use the chain rule. The partial of the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. Let's simplify this. So the partial of z with respect to y is negative x minus 2y minus 2x plus 2y, all divided by x plus 2y quantity squared. Well, again, the 2y's cancel, and so I get partial z with respect to y is negative 3x divided by x plus 2y quantity squared. Okay, and so let's determine dy dt. The derivative of e to the negative pi t is e to the negative pi t times the derivative of the exponent. The derivative of negative pi t is negative pi. Okay, so finally, we can sort of combine everything together. We get dz dt is equal to dz dx three y over x plus 2y squared times dx dt, which is pi e to the pi t plus dz dy, which is a negative 3x over x plus 2y squared times dy dt, which is a negative pi e to the minus pi t. One last. Let's do this. Okay, so this is equal to, let's simplify this. So dz dt. It's actually easier to write this, I think, in terms of x and y rather than in terms of t. So let's write this in terms of x and y. So this is going to be, let me put the pi inside. So this is 3 pi y. E to the pi t is just x. So let me write this as xy over x plus 2y quantity squared minus 3 pi, I'm sorry, so that's a plus, 3 pi x, e to the minus pi t is y, over x plus 2y quantity squared. And so I can just add these up together, and I get dz dt is equal to 6 pi xy over x plus 2y quantity squared. And that is your answer. Oh, actually, let me note one thing. Actually, 1 second here. I note the following, that x times y is actually equal to 1, because this is these are inverses of each other. And so x times y is 1, are reciprocals of each other. And so actually I can write this, okay, as dz dt is equal to 6 pi over x plus 2y quantity squared. So I can actually simplify this by using the fact that x times y, in this particular case, is equal to 1. Let me do another example. So problem number 10, I can actually move this up here. In exercises 7 through 12, use the chain rule to find partial z with respect to s and partial z with respect to t, where z is equal to radical x e to the power xy, where x is equal to 1 plus st, and y is equal to s squared minus t squared. So, first, partial z, partial s. So, z is a function of x and y. So this is partial z with respect to x. And x is a function of s and t. So partial x with respect to s, plus z is also a function of y. So partial z with respect to y times partial y with respect to s. And then let's figure out what each of these are. And so partial z with respect to x Okay, so let's use the product rule in this case. And so it's the derivative of the first times the second derivative of the first times the second plus the first times the derivative of the second. The derivative of e to any exponent is e to that exponent times the derivative of the exponent, which in this case is y. Since y is treated as a constant in this case. So, this is equal to let me factor out maybe e to the xt, and maybe also I'll factor out. So I'll write this as e to the xt over 2 rad x. Okay. So if I factor out that, I get a 1 plus, I have a y here, and then I have a x over 2, a 2x. Okay, and so then the 2's would cancel, and one of the rads would cancel. Okay, so that's, I guess I'll simplify it, writing it that way. Next, let's find the partial of x with respect to s. Well, the partial of 1 is 0. With respect to s is t. Let's do the partial of z with respect to y. So radical x is constant. The derivative e to the xt is e to the xt times the derivative of the numerator, which is x, since x here is treated as a constant. And so maybe I'll write this as partial z partial y is equal to x to the 3/2 e to the xy. Okay. And now let's take the partial of z, a partial of y with respect to s, which is equal to, well, the partial of s squared is 2s. Partial of t squared is 0. And so we get partial z with respect to s is equal to, and there should be a 2 in there, so 1 plus 2x y over 2 rad x e to the xy. That's a partial of z with respect to x. The partial of x with respect to s is just t. Plus, I had x to the 3/2. The partial of z with respect to y, e to the xy. The partial of y with respect to s is 2s. Okay, so this is equal to partial z partial s is equal to, maybe let's factor out e to the xy actually let's factor out, if I factor out a 1 over, I'll just leave that, times t plus 2x yt over 2 rad x plus 2s x to the 3/2. Okay. Now, of course, you could plug in for s and t, but it's going to look more complicated if you do that. So maybe I'll just leave it like this. So again, this is actually, I've written this sort of a complicated way, only because it doesn't look as nice. If I substitute in for both S and T, it'll just look a little worse for the wear. Okay, so let's do the partial of z with respect to t. This is going to be the partial of z with respect to x, partial x with respect to t, partial z with respect to x, a y, partial y with respect to t. And so let's figure out each of these. Partial z, I already have that. Let's not figure that out. I already have it right here. So let me actually not figure out partial z with respect to x, nor the partial of z with respect to y, because I already figured these out, and I'll just look at them. So rather than doing that, let's just figure out partial x with, so let's figure out what that is. Okay, so partial of 1 is 0. Partial of st with respect to t is s. Let's do the partial of y with respect to t. Partial of x squared with respect to t is 0. The partial of a negative t squared is a negative 2t. Okay, so I get partial z partial t is equal to, well, 1 plus 2xy over 2 rad x times e to the xy, e to the xy. That's partial of z with respect to x. All times, well, the partial of x with respect to t, which is s, plus, well, x to the 3/2 e to the xy. That's the partial z with respect to y times the partial of y with respect to t, negative 2t. And so this is equal to, oh yeah, I guess I will need a little bit more room here. Well, actually, let me just pull this down. It'll probably be easier to pull that down, to give me more space. And then I can add a new thing at the bottom. So the partial z with respect to t is equal to factor out e to the xy. So what remains is s plus 2sxy over 2 rad x minus 2t x to the 3/2. And that is your answer. Okay, good. So let's do problem number 43. I'll have to pull it up just one more line to make it look nicer. I don't really save any space, but okay. So let me do problem number 43. One side of a triangle is increased at the rate of 3 centimeters per second, and a second side is decreased at a rate of 2 centimeters per second. If the area of the triangle remains constant, at what rate does the angle between the sides change when the first side is 20 centimeters long and the second side is 30 centimeters and the angle is pi over 6? Okay, so let's do this. So I have here some triangle. Let me call this angle theta, and let me call this length A and this length B. Okay, so we have that one of the sides here is increasing by 3 centimeters. Let's say dA dt is 3 centimeters per second. Okay, and the other one, dB dt, is decreasing by a rate of 2 centimeters per second. The angle is theta is pi over 6. A is 20 centimeters and B is 30 centimeters. We want to figure out, oh yes, in the area of this whole triangle is not changing, so it's equal to 0 square centimeters per second. I want to figure out what is d theta dt, the number of radians per second. Well, I know the following. I know that the area of a triangle is just 1/2 AB times, in this case, sine theta. And so I know the area of AB sine theta. So let's figure out how this is changing. So let's differentiate both sides sides of this equation with the t. See how it's changing with respect to time. So I have that dA by the chain rule, dt is equal to well, this depends on A, B, and theta. Of A with respect to A, dA dt. A only depends on time. Plus partial A with respect to B times dB dt plus partial of A with respect to theta times dA dt. Okay, so let's do this. So, well, I know that dA dt is 0. Well, maybe I should just write it. Let me just say, before I even, so dA dt is equal, partial of big A with respect to little a is, well, let's take the derivative. So this is 1/2 B sine theta. dA dt, I'll just write it as dA dt. Then I'll put in all the values. Partial A with respect to B is just, well, 1/2 A sine theta. Just taking this partial here of A, of big A, the area, partial of the area, times dB dt. And again, we have these values. We know what these values are for some particular situation. Plus partial of A with respect to theta. Well, the derivative of sine is cosine times d theta dt. And the theta dt is what we want to figure out. So I know that dA dt is 0. I know that B is 30. I know that theta is pi over 6. I know that dA dt is positive 3. Let me just check. Yes, it is. Okay, 30 and the other one's 20. I'm just checking. I was getting a little worried if I made a mistake. Plus 1/2. A is 20. Theta is pi over 6. dB dt is -2. Let me move this all the way over because I'm going to need all that room. Okay, plus 1/2. 20 times 30. So A is 20, B is 30, cosine of pi over 6. I need even more room. Let's see if I can squeeze it just a little bit more. Okay, cosine pi over 6. Theta is pi over 6. D theta dt. Made it. Okay, good. So I just barely made it. Okay, so I get 0 is equal to um, 30 divided by 2 times sine of pi over 6 is a half times 3 minus divided by 2 is 10. Sine of pi over 6 is a half. 2 is just 2. I put the minus out in front, obviously. Plus 30 times cosine of pi over 6, rad 3 over 2, d theta dt. Okay, good. So this is equal to 15 divided times 3, 45 over 2. So 0 is equal to 45 over 2 minus 10 plus 300 rad 3 over 2 d theta dt. Let me get rid of the 2's. So I have 0 is equal to 45 minus 20 plus 300 rad 3 d theta dt. So I have 25 plus 300 rad 3 d theta dt is 0. I can actually divide it by 25 and I get 412. So this is equal to 1 plus 12 rad 3 d theta dt equals 0. So therefore, d theta dt is equal to negative 1 over 12 rad 3 radians per second. And so that is how the angle is changing at that particular instant with all these situations going on. Okay.